So the purpose of this experiment was to observe the interactions between objects containing excess charge. It was designed to allow us to become more familiar with the idea of charge and how its properties manifest within the world. So in this lab, we use Coulomb's force law and the electric field equation for a point charge to calculate the amount of excess charge on a piece of tape. The decision that was made in this model was to treat each charge as a singular point charge. This allowed us to simplify our model and make calculations easier. The main result of this was a prediction of how much excess charge was left on a singular piece of tape. To set up the experiment, we first created a base tape approximately 20 centimeters in length. We made a handle and then stuck the base tape onto the table. Our charge tape, also known as U-tape, was placed on top of this base tape. In order to give the U-tape its charge, we quickly pulled it off the base tape. It is important to handle the charged tapes as little as possible because any interaction with it could either take away or give it excess charge. After sticking the U-tape on the edge of the table, we noticed that it was attracted to our fingers within a certain distance. If the U-tapes were brought together, we would expect to see them repel. So to test this theory, we recreated two new U-tapes and slowly brought them close together. Just as theorized, the two pieces of tape were repelled by one another. We also noticed that one of the U-tapes was attracted to objects such as pens and books. Now, let's say we had a negatively charged pen. If the U-tape was attracted to the negatively charged pen, then the U-tape would have a positive charge. If it was repelled by this negatively charged pen, then the U-tape would have a negative charge. To test this theory, we rubbed a pen through hair to give it negative charge, and after observations, we saw that the U-tape was indeed attracted to the pen. Therefore, it has a positive charge. If protons and electrons switch charges, then our observations would remain the same. The tape would have a negative charge and the pen would have a positive charge and still be attracted to one another. So in this part of the experiment, we balanced the force of gravity with an electrical force by using two pieces of U-tape. We identified this system as two tapes exerting an electrical force on each other and the planet Earth causing a gravitational force on the two tapes. To set up the experiment, we placed a charged U-tape with approximately 15 centimeters in length between two ends of 2 meter sticks. We then made another U-tape and placed it right under the original tape to see if the original U-tape would move. When the second U-tape was within a certain range of the first U-tape, the first U-tape would be repelled and slightly move up. This gave the impression that the tape was floating mid-air. Since the momentum of the tape remained constant, we concluded that the net y component of the force acting on the tape was 0. This was due to the fact that the force of gravity on the first tape was being balanced by an electrical force from the second tape. If we assume both tapes to be point charges, the vertical forces on the first tape can be modeled by this free body diagram. To find the amount of excess charge, we first use the equation F equals ma to find a force of 1.47 times 10 to the negative 3 newtons. We then set the force of gravity equal to Coulomb's force law and then solve for Q. If we assume Q1 and Q2 to be equivalent, then we can square and solve for Q, getting a value of 7.7 times 10 to the negative 9. If we divide this by the charge of an electron, we can find how many electrons. So using the dimensions of the tape, we can find how many atoms were on the surface of the charged U-tape. This gives us a ratio of 1 to 4.5 times 10 to the 6 of electrons to atoms. And since we know that the U-tape is positively charged, it is deficient in this amount of electrons. So this is my computational model for the experiment, with both U-tapes representing a point charge. And the red arrow represents the electric force from the bottom U-tape onto the first U-tape, and the blue vector represents the gravitational force on the top U-tape. The electric field we get is negative 3.9 times 10 to the negative 6, pointing in a downward direction, with the force of gravity on the top U-tape and its charge agreeing with our previous calculations. The key takeaway from this lab was that electrostatic forces can be explained using an electric field model. While assumptions were made to simplify calculations, our model was a close approximation to how real charges interact. Treating each piece of tape as a singular point charge allowed us to use Coulomb's law and determine the amount of excess charge. Even though this model ignored factors such as the charge distribution on the tape's surface, it allowed us to connect experimental observations with theoretical concepts.